Hello once again, this is Richard Walker from Lucidate. In this final episode on cryptocurrencies, we will look closer at the peer-to-peer network architecture of Bitcoin. We will examine the different types of nodes that make up this network. We will also discuss some of the techniques to enhance performance and scalability. The discussion here has ramifications well beyond Bitcoin and cryptocurrencies. The techniques that help Bitcoin scale have a vast amount of use cases in the broad field of distributed finance. In common with other peer-to-peer networks, the Bitcoin network is resilient, open, and decentralized. There are no central servers or supernodes. All nodes are equal and cooperate with one another to provide network services. While these nodes are all equal, they may take on one of many different roles. These roles depend on the functionality they support and their underlying hardware specification. Only the very largest computers with dedicated ASICs, or application-specific integrated circuits, can nowadays qualify as miners. A large disk will be required to download the entire blockchain and run a full blockchain node. Yet, resource-constrained mobile devices and tiny edge computers are capable of running SPV, or simplified payment verification nodes, as we will see. The principal components of Bitcoin nodes are shown here. Network routing is the fundamental component of all nodes. This allows discovery of and connectivity to peer nodes. This also allows for various forms of validation and verification, depending on the broader capabilities of a particular node. Nodes with large storage capability can download the entire blockchain. This requires a large amount of disk space and several hours or days to download. Nodes that can download the entire ledger can check and validate UTXOs and transactions. Nodes with less resources can still perform more limited validations using some of the techniques, such as Merkle trees and Merkle proof, that we will discuss later on in this video. Mining nodes need specialized hardware in the form of application-specific integrated circuits. Only very powerful, energy-hungry, specialized hardware can generate the hashing power necessary to be a miner. Wallet software is able to search the ledger for UTXOs to serve as inputs to transactions, or to determine the balance that a Bitcoin user has. Combinations of these components then give rise to some typical configurations. A Bitcoin core reference client. This implements all aspects of the Bitcoin system. A wallet, a full copy of the ledger, a mining and verification engine. A full node. This is the traffic cop that we've spoken about in earlier videos. This will keep a full copy of the ledger, so we'll need a large amount of dedicated disk space. The ledger grows at a predictable rate of around 1/2 to 1 megabyte every 10 minutes. As of spring 2022, the ledger is around 400 gigabytes. A mining node. This needs a copy of the full ledger, complete with the UTXO set and some dedicated hardware to produce the required hash rate. At the other end of the spectrum from a miner is an SPV node. SPV stands for Simplified Payment Verification. For cryptocurrencies like Bitcoin to succeed, they can't rely solely on expensive, power-hungry rigs. SPVs are designed to run on resource-constrained systems like mobile devices and tablets. We'll talk later in this video about the technology deployed to enable this. This SPV configuration does not maintain a copy of the entire ledger. As we will see, it uses some interesting techniques from cryptography. It receives data from peer nodes that do maintain a full copy of the ledger to perform some limited but thorough checks on transaction integrity. All these nodes connect to one another via peers. Thus, the entire Bitcoin system is a loose affiliation of distributed systems of varying specifications. Each node provides resources and services according to its capabilities and limitations. Nodes join and leave the network continuously. Accordingly, each node will try to maintain connections with a handful of other peers. In the rest of this video, we're going to focus on the SPV nodes. We can build more scale if we design systems that can encourage as many participants as possible, reducing barriers to entry by lowering the hardware specification makes the network stronger through diversity. We gain resilience and redundancy through decentralization and broad participation. Remember, this is a collaboration. SPV nodes can't function on their own. They need peer communication with full nodes as well as with miners to be able to contribute to the protocol. To recap, SPV nodes are lightweight. They perform no mining, nor do they carry a complete copy of the ledger. For them to be effective, we need a mechanism for SPVs to confirm that transactions are valid. They will also need to calculate things like a user's balance, that's to say the sum of all their UTXOs, as well as build transactions from the UTXO set to pay other Bitcoin users. How might they accomplish this without a full copy of the ledger and the entire UTXO set? As a lightweight node without large amounts of local storage, two things are at a premium. One, the amount of data held locally. Two, the amount of data broadcast over the network from full nodes to SPVs. The Bitcoin block header is small. It contains exactly 80 bytes of data. With a new block being mined every 10 minutes or so, this means that block headers grow at around 4.2 megabytes a year. With mobile phone storage being measured in gigabytes, storing all of the block headers will be well within the scope of SPVs. If we look at the block header, that we can see that one of the values is called a Merkle root. What is this variable and why is it there? What it is a SHA-256 hash of all of the transactions in the block. It's built up by first getting the SHA-256 digest of each transaction as a 32-byte string. Then, starting with the hash of the Coinbase transaction, we pair each transaction digest. If there are an odd number of digests, then we simply copy the final digest to pair it with itself. We then concatenate each pair of hashes into a 64-byte string and apply the SHA-256 algorithm to that concatenated string. This results in a set of hashes half as big as the original set. We then do the same thing again and again and again. Concatenate each pair of digests into a 64-byte string and hash again, remembering to copy the last digest if we have an odd number, so it makes a pair with itself. We carry on this process of pairing and hashing, pairing and hashing, pairing and hashing, until we're left with only one digest. This is called the Merkle root. A hash tree like this is called a Merkle tree, named after Ralph Merkle, a prominent computer science polymath who patented this structure in 1979. The Merkle root is unique for this set of transactions. If you change just one character in any of the transactions, or even change the order of the transactions, then the Merkle root will be completely different. You can't derive the transactions from the Merkle root, but you will get this exact Merkle root from a specific set of transactions. It's the unique digital fingerprint for the confirmed transactions in this block and ensures that they're not tampered with. Here's the clever bit. If you want to know that a transaction is in this block, you can get a full node to prove that it is. You don't have to trust any particular node. Instead, you can rely on rock-solid cryptographic proof. If you're a receiver of Bitcoin, then you'll see a transaction that contains UTXOs as inputs and an output to your address. You will want to make sure that the input UTXOs came from valid transactions. If you're running a full node, then this is simple, as you have access to the entire ledger. But as an SPV, you don't have this luxury. Instead, to prove a transaction is in a block, you can request the Merkle path for that transaction. The Merkle path is the sequence of digests that this transaction was paired with in the Merkle tree. Once an SPV has received the Merkle path from a node, it can check for itself that the transaction is valid. In this case, we're interested in transaction H in this block. First, the SPV can generate the digest or hash of this transaction by applying SHA-256. Then it can concatenate this digest with the first string in the Merkle path and apply SHA-256 again. This is then repeated with the next string in the Merkle path. Concatenate this string with the digest just created and run SHA-256. This pairing and hashing, pairing and hashing, pairing and hashing can continue until there's just one pair left. The SPV node can then compare the SHA-256 digest of this pair to the Merkle root for that block. If the valid transaction was in the block, the two strings will be identical. Each transaction will have a unique path from the leaf node to the root node. Thus, each transaction will have a unique Merkle path within that block. There is no chance that a dishonest node could come up with the exact sequence of hashes in the Merkle path that would result in a match of the Merkle root. This proves that the transaction was in the block. The amount of data that a node needs to send to the SPV is also small. The number of strings in the Merkle path will likely be 10 or 11, depending on how many transactions are in the block. The Merkle tree thus provides a very compact way for a node without a ledger to prove that a valid transaction exists within a confirmed block. To see how compact it is, look at an alternative approach. Instead of building the Merkle tree from all the transactions in a block, you could store the hashes of all the transactions in the block header. For a block containing 1,500 transactions, that would mean that the header is just over 40k in size, but this is much larger than the 80 bytes in a header containing the Merkle root. Quite a scaling. Both these methods are clearly more compact than the block itself. Most transactions sit in the 400 to 600 byte range, meaning that a typical block is 750 to 800 kilobytes in size. This simplified payment verification strikes a balance between practicality and security. There is a small possibility of double spend. If complete security is desired, then waiting for a set number of confirmations would be the best approach. A good analogy in trust-based systems for SPV is an old-school check. One will be happy instantly taking a check for a small amount, but might want to wait until the check had cleared for larger payments. A more modern analogy might be contactless payments. These are valid for smaller payments without any other form of ID, but for larger amounts there may be the need to supply biometrics on a phone or provide a PIN. To conclude this video and this series, let's take a look at a Bitcoin block explorer. This will illustrate some of the concepts introduced in this video series. Here's a sample from blockchain.com/explorer. On the right of your screen are the latest blocks to be mined. Let's take a closer look at the last block but one. This is block 738,975 in the chain, mined on June the 2nd, 2022 at 9:53 AM British summertime. You can see the block header hash along with the leading zeros. Also of significance is the hash of the Merkle root, the mining difficulty, and the nonce for this block. If we scroll down, we can see a list of the block transactions. This begins with the Coinbase transaction. The block reward for this transaction is 6.25 Bitcoin. We can look at the transactions in this block by clicking on the transaction hash. This hash will be Merkleized, if indeed that is a verb, with all the other transaction hashes. This will result in the Merkle root for this block, which you saw just a minute ago in the header. We can see that this transaction has a single input and 3 outputs, one of which has been spent in a later block, and 2 remain unspent as UTXOs. We can look at the address of the recipient of one of the UTXOs. This is derived from the public key of this participant and may only be unlocked or spent with this recipient's private key. While this data is anonymous, that's to say we don't know who this user is, all the information is public on the ledger. Hence, we can see a transaction history and a balance for the user of this address. Our hope at Lucidate is, having seen this series of videos, there's nothing in this block explorer that is surprising, mystifying, or confusing. This series has introduced public and private key cryptography and hashing, which, when used together, helps digitally sign documents and produce the chain of signatures that Satoshi described in the 2008 paper. We've explored UTXOs, blockchain, and proof of work, which together help us solve the double spend problem. We've looked at the design of the Bitcoin network and how this design makes it extremely resilient to attack, fraud, and other malicious uses. Finally, in this video, we've looked at how to scale the network to handle mobile and edge devices. These don't have the computing power or storage capabilities of full nodes or miners. In this regard, a clever use of Merkle trees, which also use cryptographic hashing, has been shown to be very effective in compressing the amount of data required to prove the existence of a transaction. While this series is focused on Bitcoin, the principal purpose has been to explain some of the core components of decentralized finance, DeFi. I hope that this series of 6 videos has inspired you to consider some of these exciting approaches to cut the costs in trust provision in your business. If you feel that Lucidate can help in providing consulting, strategy advice, or education for your DeFi initiatives, then please contact us by using any of the means on your screen. Many thanks for watching.